continue.
So good afternoon to one and all present over here. I, Mrs. Jayashree Basak, Assistant Professor, Department of Computer Science and Engineering, Surendra Institute of Engineering and Management, Siliguri. And I'd like to welcome you all to this webinar session. Firstly, I would like to express my gratitude to the Principal Sir, Chairman Sir, Director Ma'am, and the Management Committee of this organization. With due permission of Honorable Principal Sir present over here, we are going to start our today's online tech seminar on asymptotics of some large-scale network, which is jointly organized by the Department of Computer Science and Engineering and Electrical Engineering of SIEM Siliguri. In today's world, large-scale networks like cloud data centers, social networks are present everywhere. Asymptotic analysis of such network often provides interesting insight into their behaviors, which are useful in practical system design. So, I think this online tech seminar will be very much useful for all of us. So, I would like to request you all to stay connected up to the end. Now, I'd like to request Mr. Shubhadeep Shaha, the HOD of Electrical Engineering, to deliver the welcome speech. Over to you, sir.
So, very good afternoon to all of you present here. Honorable Chief Guest Dr. Arpan Mukhopadhyay, Assistant Professor, University of Warwick, United Kingdom. Honorable Chief Guest Mr. Kanchan Roy, Business Analyst, Wipro. Honorable Chairman Sir, Mr. Sharad Agarwal. Honorable Director Madam, Mrs. Snigdha Agarwal. Honorable Principal Sir, Dr. S. Nagarajan of Surendra Institute of Engineering and Management, Siliguri. And Honorable Head of the Departments and dear faculty and staff of Surendra Institute of Engineering and Management, Siliguri. And dear students and ladies and gentlemen, myself, Shubhadeep Shaha, heading the Department of Electrical Engineering, and along with me, Dr. Papri Ghosh, HOD of Computer Science and Engineering, Surendra Institute of Engineering and Management, Siliguri, are the conveners of this webinar. We are happy to welcome all the people very warmly. We would like to express our gratitude to our respected panelists who accepted the invitations. Today, all of us have gathered here to learn and listen a very important topic, that is the asymptotics of some large-scale network, from our honorable chief guest, Mr. Arpan Mukhopadhyay, Dr. Arpan Mukhopadhyay. So we are very confident that this webinar will be very successful like every semester, and we request your cooperation to make it memorable. Thank you.
Thank you, sir, for your wonderful speech. So now I'd like to request Honorable Principal Sir to address this gather. Over to you, sir.
Thank you, Jayashree ma'am. Is my voice audible?
Yes, sir, properly.
Okay, thank you. Distinguished chief guest and resource person of today's session, respected chairman sir, director madam, beloved students and my dear staff members, good afternoon. Today I sit before you with extreme pleasure on behalf of student club of Surendra Institute of Engineering Management. During last semester, we have inaugurated various student clubs. Through student club, regularly we are conducting programs for the benefit of the students. So in this contest, we are also arranging webinar for CSE electrical students today. First of all, let me express my deep gratitude to you all for supporting me for implementing various teaching learning process in our campus, especially during this pandemic period for the benefit of the students and faculty members. We have successfully completed more than 100 programs during this pandemic period, and many students from neighboring institute, outside states and outside country also attended and benefited out of our program. Today, we have come out with one more program for the benefit of students, electrical and computer science engineering students. I convey my gratitude to the chief guest of today's session, resource person, for accepting our invitation to deliver a keynote talk on the chosen topic. So on this occasion, I congratulate both electrical and computer science engineering department and their team members for successfully organizing the webinar to enrich students' knowledge in the emerging technologies. I hope this kind of program will help the students to get a wider perspective of their field of domain. And my sincere appeal to third and final year students, when you do your mini and major project, please take your project very seriously and sincerely. And once you complete your final year projects, as well as your mini project at third year level, please go for presentation like a symposium, either national, international symposium or conferences. That will give you confidence, and you will also get some feedback from the expert members, so that you can fine tune your work, so that you will get much better knowledge in the respective field of domain. I strongly believe that through your project you can able to get some good opportunity even during this pandemic period. When we had a discussion with the HR people, they keep telling that we are looking for some good uh, eligible students for the company. But other side, we are talking about unemployment issue, and there is no job during this pandemic period. But the main problem with the current scenario, companies are not ready to fund for any kind of training program. They are looking for ready product. So if you have enough knowledge in the respective field of domain, especially in the latest technology, you'll be directly employable for the particular company. So my request to all the student over here, when you do your project, please choose your title which is more appropriate to the latest trend, so that once you successfully complete your project, you can able to grab some good opportunities from the leading companies. Hence, I request you all to take up your academic session very seriously, so that you can complete your course with good grade point. That is also very much important, because the first level of screening purely based on your academic performance. So you have to be uh, good in both academics as well as your hands-on session. And recently we have received notification from university, our markout university, regarding the article writing competition on account of Environment Day. Same may be communicated to all the HODs. I think you might be knowing the competition details and other things. So if you have any doubts regarding this, you can feel free to contact your HOD, so that you can submit your article before the deadline. And finally, I would like to thank both HODs, electrical engineering HOD and CSE HOD, for organizing such a wonderful session for the benefit of the student. So with that small introductory message, I once again wish both faculty member and student, you will be having a fruitful session for next 1 hour. Thank you so much for the opportunity. Over to the moderator.
Thank you, sir, for your inspiring messages. So now it is a great pleasure today for me to introduce our honorable chief guest, Dr. Arpan Mukhopadhyay, the Assistant Professor, Department of Computer Science, University of Warwick, UK. He has received Bachelor of Engineering in Electronics and Telecommunication Engineering from Jadavpur University, India in 2009. He has completed Masters of Engineering in Telecommunication from the Indian Institute of Science in 2011. He has received PhD in Electrical and Computer Engineering from the University of Waterloo, Canada in 2016. He is currently an assistant professor with the Department of Computer Science, University of Warwick, UK. His research interests include applied probability, stochastic processes, algorithm design, and optimization with application to complex network analysis. He was a recipient of Best Paper Awards from the IFIP Performance in 2015 conference and the International Teletraffic Congress ITC in 2015. He also received the Rising Scholars Award at the International Teletraffic Congress 2018 for his contribution to mean field analysis of large heterogeneous network. So we are really thankful to him for taking the time out of his busy schedule to attend this virtual tech seminar. Once again, welcomes you, Dr. Arpan sir. I request you to share your valuable knowledge with us. Over to you, sir.
Thank you very much. Let me share my screen so that you can see my slides. Can you see my slides now?
Yes, sir, your slides are visible.
Okay, thank you very much. Good afternoon, everybody. Good morning, depending on where you are listening from. I'm very happy to be here and thank you for the invitation. And I'm looking forward to an exciting session. And I hope to share some of my knowledge with you. So the title of my talk today is on the asymptotics of some large-scale networks. So there are two keywords in the title of this talk, as you can see. The first keyword is asymptotics, and the second one is large-scale networks. Now, one may ask, what do I mean by large-scale networks? And what do I mean by the asymptotic properties of such large-scale networks? I hope to answer these questions during the presentation, but just as a starter, I would like to briefly say that large-scale networks are networks consisting of a large number of interconnected nodes. For example, the internet or social networks, these are examples of large-scale networks. And the word asymptotics in the title refers to some properties of these networks that emerge as we scale up the size of the networks. So as the networks grow in size, these properties emerge. So the talk will essentially focus on these asymptotic properties of some specific large-scale networks. And we'll also see why studying such asymptotic properties are actually important in real system design. Okay, so this is an outline of my talk. So I will start with a very brief overview of large-scale networks and their asymptotic properties. And then throughout the rest of the talk, I will specifically focus on the asymptotic properties of two specific types of networks, namely caching systems and social networks. So this is the overall outline. By the way, if you, I will try to make my talk as general as possible so that even non-specialists can follow my talk. But at any point, if you have any question, please feel free to raise those and interrupt me during the talk. So I'm happy to answer all your questions. Okay, so this is an outline of my talk. And so I'll start by giving some examples of large-scale networks. The first example is of content distribution networks. So these are networks consisting of cache servers that are distributed across the internet. So what do these servers do? They store popular internet content such as, say, YouTube videos or Netflix movies and so on. So these are highly popular contents, and instead of accessing these contents right from the origin server, for example, if I want to access a YouTube video, I do not have to always go to the main YouTube server and fetch that video from there, but instead I can just fetch it from a cache server, which is much nearby to me than the origin server. So these cache servers provide a quick access to the same contents by caching some popular contents into those servers, those network servers. And the network of such cache servers is called content distribution networks. And many companies provide such networks. For some big names in this domain are Limelight and Akamai. This is one example of content distribution of large-scale networks, and we'll see more coming up. Second example is of cloud data centers. Now, you may be already familiar with this name. Cloud data centers are networks of thousands of servers connected together and serving millions of jobs submitted by users every second. So instead of using our own PCs or computers at home, we might want to run our programs on a cloud service. And most big companies like Amazon, Microsoft, or Google provide this kind of service to users. So instead of running our jobs on our own machines, we can submit the job to their service over the internet. And what they provide is this network of a huge number of servers. And when we submit our job to the systems, their duty is to place the job in one of these thousands of servers and run it as quickly as possible. So this is, again, another example of a large-scale network because there are a lot of servers in their system in general. The third example is social networks. So most of us are familiar with some kind of social network. So big examples are Facebook and Twitter. And we can think of these as networks of connected social agents where social agents interact with each other via their connections. And the last, but not the least important one, is the example of energy systems. Now, energy systems can be thought of as networks consisting of generators, transmission lines, transformers, etc., which provide and deliver power to our homes and offices. So they can also be thought of as some kind of networks. Now, as computer scientists, we are often faced with some important design questions pertaining to such large-scale networks. For example, in the context of a content distribution network, one may be interested to know how we can replicate popular content such as YouTube videos or Netflix movies across the cache servers such that we can ensure that these contents are easily available to the users. So this is a typical design question that we would face if we work for a content distribution network provider. In a cloud data center, a key question is how we can assign a user request to the thousands of servers running all the time inside a data center. And our goal in this case would be to minimize the average delay seen by a user. In case of a social network, one may be interested in knowing how information can spread via social interactions. And this can be useful for a marketing company, for example, if it wants to market its product on a social media platform. And in the context of energy systems, it may be interesting for a grid operator to know how to control their grids under the uncertainty of renewable sources of energy, such as wind and solar. So all these are design questions, but in general, each of these questions is difficult to answer, and it requires solving some hard computational problems, and perhaps involving some sophisticated mathematical modeling, simulation, and experiments. But in some cases, this analysis can become easier as the network sizes grow. So this may seem a bit counterintuitive in the beginning, because we expect that a problem which is already complex for a small system will become more complicated if we add more nodes to the same network, or if we grow the size of the system, it is expected that the problem will become more complicated to solve. But what we see is the opposite of this intuition, that some of these problems actually become easier to solve when we grow the size of the network. So it is easier to solve these problems when we assume that the size of these networks is very big. So in that sort of a limiting situation, I will show that some of these questions are actually easier to solve. So instead of focusing on all these questions, I will not have time to answer all of these questions, but I will try to focus on two specific systems. And these two specific systems are here highlighted by the rectangles. So I will try to answer the caching system, or the content distribution network systems, and try to address the question of how to replicate contents, ensuring their high availability. And also in the context of social networks, I will try to address the question of how information can spread via social interactions. And I'll try to answer these questions by studying the asymptotic properties of these networks. So these are, again, as I mentioned in the beginning of my talk, asymptotic properties mean the properties which emerge when we scale up the size of the networks. So we will study such properties for these specific networks and try to answer these design questions from those properties. Okay. So this completes the overview section of my talk, and now I will jump to more detail of these two specific systems one at a time. So at this point, is there any question that you have? So the way my screen is shared, probably I will not be able to see your hands. So please, if you have any question, please feel free to just unmute yourself and ask that. If you don't, then I'll just move ahead with my slides.
Sir, you can move. No questions.
Okay. So if there isn't any question at this point, so I'll just move on. So the first system that I will focus on, as I mentioned, is caching systems or content distribution networks. So I will call them as caching systems. That's a more general term, because the servers in a content distribution network are essentially caching servers, and therefore we call it a caching system. And the thing I'll talk about is a result of two publications that I had jointly with Marc Lellert from INRIA Paris and Nidhi Hegre, who's from University of Alberta. And these were published in Infocom in 2018 and IEEE Transactional Networking in 2019. So before we start, some motivation behind studying this problem. So we all know about video streaming services such as YouTube and Netflix. And it is predicted by Cisco that by the year 2022, almost 82% of internet traffic would be due to such services. So we clearly have the motivation of designing distributed caching systems which reduce the burden on the YouTube and Netflix servers by replicating some of these popular contents across cache servers which are at the edge of the internet. So by edge, I mean the part of the internet which are closer to the user. So instead of going all the way to the YouTube or Netflix main server, we can directly access these contents from some edge servers that are much nearer to a user. So these are called caching servers, and the system of caching servers is called a caching system. So the objective of designing a caching system is obviously, as I mentioned, the main objective is to reduce the load on the contents provider's main servers. So in this case, the content provider is either YouTube or Netflix. And we also want to make sure that if the main servers are down for some reason, for example, if the YouTube server is down or the Netflix server is down, then we can still access the contents from these edge servers where the popular contents are already stored or cached. So that's another objective of designing caching systems. And the third objective, as I mentioned, is to bring the contents closer to the users. So typically, there are very few main servers of YouTube or Netflix across the world, but the users are spread across the whole world, and they're accessing these contents from almost anywhere in the world. And therefore, it will be definitely helpful if we can bring these contents closer to the users by replicating them into the cache servers. Okay, so these are the main three objectives of caching system. Now the question is, how do we model? So if we want to study a design question related to any system, for that matter, we have to sort of have a view of or a simplified view of the system and focus on the question that we want to answer. So in this case, this is the simplified view that we will consider. So this is how typically a caching system or a CDN or a content distribution network looks like. So we have here, so let me show my pointer. So we have here this system of cache servers. So I'm showing it by this cloud here. So inside the cloud, we can see a lot of CPUs. And these CPUs are basically representing my cache servers. And each of these cache servers are storing some video contents, as you can see. So and above all these small cache servers, we have this main content provider servers, which are maintained by YouTube and Netflix. And this network of cache servers is maintained by the content distribution network providers, such as Akamai. So Akamai will control the smaller servers, and YouTube and Netflix will have this main servers. So the goal of this cache servers will be to take some of the popular contents from this main servers and replicate those contents across these smaller cache servers. And these are supposedly closer to the users than the main servers. So whenever a user submits a request for, say, a video content, it will first come to this content distribution network, and the content distribution network will try to find a match between the request and the server. So it will try to find a server where this particular content is stored, and then route that user request to that particular server. So for example, if a user has requested this particular video, then it can be routed to this server or this server also, because this server also has the same video. Now, if a requested video is not there in any of these servers, that means it has to be accessed from the main content provider's server. So, so that is obviously more expensive because we have to go a longer way to access that particular video. So that is not desired. So we have to minimize the fraction of requests that have to go to the main server to access those contents. So that's the main goal that we will focus on. So our goal, as mentioned here, would be to maximize the fraction of requests served by the cache servers, and therefore equivalently minimize the fraction of requests that are lost from the caching system and that goes to the main server. So we'll call these requests as lost requests. So these are lost from the caching system and they're going to the main servers for their service. And we will also assume that there is no queuing in the system, which means that once we submit a request, it will not be stored in any queue for servicing later. So as these are video contents, the users would like to be served immediately. We will not like to wait in a queue and then service later, but rather we would like to be served immediately as we have submitted the video content request. So there is no queuing in the system. Okay, so this is a rough overview of how a content distribution network looks like. Okay. Now, what are the design challenges for such a system? So obviously, for any system, there is some constraint. In this case, the main constraints are the memory and the bandwidth. So each server in a caching system or within a content distribution network has a fixed memory. Okay, so it can only store a limited number of contents. It cannot store, for example, the entire repository in YouTube. So all the videos in YouTube is, I don't know, it's thousands of terabytes of data that cannot be stored within a single cache server. Each server can store only a fraction or a small number of these contents, and obviously that's a constraining resource. If we were able to store all the contents in one cache server, then we would not have the problem. But because we have a fixed small memory, we have to use it efficiently, and this resource memory is used or managed by a replication algorithm. So this replication algorithm decides which content to be stored at which server. So obviously we cannot store, as I just mentioned, memory is limited. We cannot store all the YouTube videos in one server. We have to sort of decide which content to store at which server because the memory is scarce. So that's why we have to decide which replication algorithm that we will use to replicate the contents across the servers. And at the same time, another constraining resource is the bandwidth. Okay, so bandwidth means that we are able to serve only a finite number of requests at the same time from a given cache server. So a cache server do not have infinite bandwidth, so it cannot serve. So suppose 5 users are trying to access a content from a server, from a cache server. But the server may be only able to serve 3 requests at the same time. So 2 of them cannot be served by that server. So they have to either be routed to the main servers or they have to be routed to some other server in the caching network. So that's another important constraint in a caching system. And we have to manage it efficiently, the bandwidth. And we manage it by using a proper matching algorithm. Now, what a matching algorithm does is that it decides once a user submits its request for a content, which particular server would it be assigned to. So obviously we assume that we know that each server is able to only serve this many contents or this many requests simultaneously. So if a server is already serving at its maximum capacity, we cannot assign any more requests to that same server. So a matching algorithm has to take care of the fact how much of the capacity of a server is already being used, and based on that, assign new requests to the servers. So that's the job of a matching algorithm. It manages the bandwidth of the servers. Now, our goal would be to, tweak these two knobs. So we can think of, so we have to design our system as efficiently as possible. And our goal, as I mentioned before in the slide, is to maximize the fraction of requests that we will serve with the help of the caching system. Now, we will have two knobs that we can tweak to design our system. So one of the knobs is our replication algorithm, and the other knob is our matching algorithm. So by choosing a proper combination of these two, we will try to optimize the performance of the system. So we will try to maximize the number of requests that can be served by the caching system itself, so they don't have to go to the main server for their service. And our basically our knobs are these replication algorithm and the matching algorithm. Okay. So moving on. So here is a brief literature review on caching systems. So if we look at the literature on caching, we see that there are two main trends of the papers that are written on caching. On the left-hand side, I have listed a few papers which try to analyze the performance of caching systems by neglecting the bandwidth constraint. So all these papers on this side will assume that the bandwidth is infinity. So that means it will assume that each cache server can service infinite number of requests at the same time, which is not obviously practical, because each server in the caching system can only serve a finite number of requests simultaneously. So, but to simplify their analysis, these papers assume infinite bandwidth, but obviously this is not what we want. But there is another trend of papers, which I'm showing on the right, which do assume finite bandwidth, but for them, the only knob available is the matching algorithm. So in the previous slide, I discussed two knobs in the system. One is the replication algorithm, which decides which content to store at which server. And one is the matching algorithm, which decides once a user requests content, which server to assign that request to. So these are the two knobs. But these set of papers that I'm showing on the right only assumes there is one knob. So they fix the replication algorithm, and then they try to find the best possible matching algorithm for which the system performance is optimized. Okay, but our goal is to really tune both the knobs together such that we can find the best possible performance of the caching system. Okay, so here, just to reframe what I said so far. So our goal would be to present a unified framework for the study of jointly optimal replication and matching algorithms. So that means we want to design a caching systems which is optimal with respect to both replication and matching. So we will turn these knobs together to find the best possible combination. And the specific questions that we would like to address are the following. So first question is what is the best possible performance? So so under any combination of matching and replication algorithm, what is the best possible that we can achieve through a caching system? And then the next question is, can we achieve that best possible performance? So we can obviously get a lower bound of or a higher upper bound on the best possible performance. And then the question we would like to address is, can we achieve that upper bound? Okay, by tuning those knobs or by any combination of those replication and matching algorithms. And then the third question is, what happens if we scale the system? That's why we mentioned this keyword asymptotics in the beginning of my lecture. So our goal would be to study all these questions when the network size is growing. So as we grow the number of servers in the system, what happens? So what happens to its performance if we grow the number of servers or number of caching servers in this system? Okay, so these are the questions that I'll be interested in. So to answer this question, the way we would do it is, first we will build a mathematical model of the caching system, and then we'll try to analyze this mathematical model using some techniques from optimization and probability theory, and design our algorithms, and then study what is the performance of this caching system under those algorithms. Okay, so here is our mathematical model of the caching system. So here on the left hand side, I'm showing the servers, which are denoted by this CPUs on this left hand side. So I'm calling the set of servers by this notation S, and there are n of them. So there are capital N servers. All of these are cache servers. And on the right hand side, I have some contents. I'm assuming that there are M contents, capital M number of contents. And these set of contents will be denoted by this letter C. Okay, so these are my videos, basically the files that I want to access. Now, each server S has a finite memory of DS, which means that server S will only be able to store DS number of contents at its memory or at its cache. Okay, so for example, server 1 can store D1 contents, server 2 can store D2 contents, and so on. Server N can store DN number of contents. And also, we would like to impose the bandwidth constraint on each server, which means that we will assume that each server S will have a bandwidth constraint of US, which means that it will be able to simultaneously serve at most US number of requests at the same time. Okay, so if there are more than that many requests, it cannot serve. Okay, so that's the bandwidth constraint imposed on each server. So this is how we model a caching server. So we impose a memory constraint and a bandwidth constraint, which are denoted by DS and US. And we also assume that the request of each content C arrives at a rate lambda C. Okay, so what do I mean by rate? Rate means the average number of requests per unit time. For example, per units per second, how many requests of a content is arriving? It's the rate of that or it's the arrival rate of that content, which is also indicative of the popularity of the content. So if the arrival rate is high, that means the content is very popular. Okay, so I am denoting these rates by lambda 1, lambda 2, etc. And we also assume here that the service times are independent and identically distributed random quantities with unit mean. Okay, so this is a technical assumption. I will not go into too much detail, but it means that on an average, each request user submits will take 1 unit of time to complete. Okay, so this basically is a base. That means that each user will stay in the system on an average 1 unit of time. Okay, that's what it means. All right, so moving on, this is our system model. And so we have to decide which content to store at which server. Okay, so that's my replication algorithm, as I described before. Now, how can I describe a replication algorithm mathematically? So that's what I'm going to address now. So a replication algorithm can be represented completely by a binary matrix, which we will denote by capital A, as shown here. The entries are ASC. Now, ASC means S stands for the server and C stands for the content. Okay, so ASC is set to 1 if we store C, content C, at server S. Okay, so that variable ASC will be an indicator of whether a content C is stored at server S or not. If it is stored, then it is set to 1. If it is not stored, it is set to 0. And we will save this collection of variables in this matrix called capital A. And this essentially determines our replication algorithm. So any replication algorithm or any assignment of the contents to the servers can be just described simply by this matrix capital A, which we will call as replication algorithm. And for any feasible replication policy, we must ensure that we are satisfying the bandwidth constraint, the memory constraint. So that means the number of contents that we store at a given server must be less than the memory size of that server. So here I am summing up the variables ASC for a given server S across all the contents. So that sum is basically indicative of how many contents this particular server is storing. And that obviously must be less than the capacity, memory capacity of that server, which is denoted by DS. So for any feasible replication policy, we must satisfy this inequality constraint, that the sum of ASC for a given S must be less than or equal to D of S. Okay, so that's my constraint for any feasible replication policy. Now, now we are in a state where we can describe the problem, or we can formulate the problem of maximizing the fraction of requests that is served by the caching system. To formulate the problem, we have to consider a unit interval of time. Okay, so let's consider a unit interval of time, and let's consider the requests that arrive within this unit interval of time. So we will denote the number of requests of content C that arrive within this unit interval by this letter XC. Okay, this is a random quantity because we don't know a priori how many requests of each content will arrive within a given unit interval, right? So this is a random quantity, and so X is random, and the vector X, which is consisted of these components XC, we will denote it by capital X, and this vector will be called as the demand vector, right? So this is the demand within that unit interval of time. Now, remember, our goal is to maximize the number of requests that are served within the unit interval. So I would like to serve as many requests as possible from this demand vector X. Okay, so XC is the number of contents, number of requests for content C, and we would like to serve as many as requests as possible. Now, remember that we said the average arrival rate of content C is lambda C. So average is denoted by the symbol expectation. I hope you are already familiar with this. So expectation of this random variable XC is given by lambda C. Okay, so that's the average value of this quantity XC, because these are random quantities. Now, to formulate the problem of maximizing the the number of requests that we can serve by the caching system, we first denote by BSC the requests for content C that are assigned to server S within this time interval. Okay, so BSC is the number of requests of content C that are served, that are assigned to server S to be served within this interval. So for example, here I'm showing that so there are some requests of this particular content that has arrived within a unit interval, and 2 of them are assigned to this particular server. So BSC for in this case is given by 2. Okay. And again, I can formulate this matrix consisting of these entries BSC, where S varies in the set of servers and C varies within the set of contents. And so we can construct this entire matrix B consisting of these entries. And we will call this matrix as the matching. Okay, so we will call it as the matching. So because we are matching the requests of users to the servers, that's why this whole matrix is deciding how we are matching the requests of users to the servers, and therefore we call it matching, and we will denote it by capital B. And our objective is to find out the optimal B. Okay, so that's what our goal is. Now, to write it more precisely, so suppose we have already decided which content to store at which server, or in other words, suppose we have already decided our replication policy or replication algorithm. So suppose we denote it by capital A, as I described in previous slides. And suppose that I have this demand vector X within that unit interval. And then my goal is to find a proper matching, capital B, such that most of the requests are served, right? So what does that mean mathematically? What does it mean to have most of the requests served by the caching system? Now, the number of requests served by the caching system is given by this summation. Now look closely at this summation here. So this is basically sum over ASC times BSC. Now, what does this summation denote? It's basically the total number of requests that are served within this unit interval of time. And we want to maximize that by choosing the right B matrix. Okay, so that's basically my objective. So to maximize the number of requests that are served within this unit interval. Now, you may ask, how is it that this quantity is denoting the total number of requests served within that unit interval? Now, it is very easy to see. Why? Because ASC is an indicator variable. It's a binary variable, either 1 or 0. And BSC is the number of number of requests of content C that is being served by server S within that interval. So we can serve content C at server S only if ASC is 1, right? So if ASC is 0, obviously we cannot serve it. So therefore we must have this multiplication by ASC here, because that indicates whether the content is there in the server in the first place. And if it is there, then BSC denotes the number of requests that are being served by server S of content C. So now if we sum it across all the contents and all the servers, that obviously gives me the total number of requests that are being served within that unit interval of time by the whole caching system. And this is what we would like to maximize as a function of this matching policy B. So this is given the A. So I'm assuming that I have decided what replication policy I will use, and then I'm trying to decide what matching would optimize this quantity. So this is maximization with respect to B only. Now, as I mentioned before, I have to respect the constraints of the system. So one of the constraints I mentioned is the bandwidth constraint. So the sum of the total number of requests that I can serve by a particular server. So this is the sum BSC for a given server over all the contents. And that sum must be less than US, because I said that each server is only able to serve up to US requests simultaneously. So this is obviously, this must be satisfied at any point of time. Okay, so that this is one constraint. And the other constraint is that we cannot exceed the number of requests that has arrived within a unit interval, right? So if we sum all the requests of content C within that interval, then that quantity cannot exceed the total request that has arrived. So XC, as I mentioned before, is the total number of requests of content C. No matter how we distribute those requests to servers, this sum cannot exceed the number of requests that arrive. So that is trivially another constraint of this optimization problem. And the final constraint is the fact that BSC are non-negative integers. So this is the notation for that. So here, what I have formulated is the matching problem. So here I am given the replication policy, and I'm trying to decide the optimal matching policy for this system. Okay, I hope this is clear. If you have any question, please raise them. But if it is fine, then I'll just move on. So here we have this optimization problem. Now it can be shown that this, since you're most of you, I assume that you are familiar with bipartite matching algorithms. So because you're from a computer science background, I'll presume that you're already familiar with this concept. So this particular problem, which looks like an integer optimization problem, can be actually mapped to the maximum bipartite matching problem, which many of you are already familiar with. So this is, and we already know that there are very efficient algorithms that can be used to solve the bipartite matching problem. So we can actually have polynomial time algorithms that can solve this bipartite matching problem. Okay, so so given replication policy A, capital A, it is actually very efficient. We can actually solve this matching problem very efficiently. Now keep that in mind, but this is not our final goal. Remember at the beginning I said we have two knobs to tune. One is our replication algorithm and one is our matching algorithm. Here we are just turning our knob for the matching algorithm. But what about the replication algorithm? That we need to turn in order to find the best possible replication algorithm, right? So this is exactly what I'm going to do now in the next slide. So this is our final problem that we want to tackle. Okay, so here not only we are tuning the B, but we are also maximizing this quantity with respect to A. So we are tuning both A and B such that we are maximizing the total number of requests within this interval of time, within that unit interval of time. Okay, so this is the total number of requests served within an interval, and we are maximizing it with respect to both A and B. But we have to obviously satisfy our constraint. We cannot choose any A or any B. They have to satisfy these constraints. And also, we have to satisfy the memory constraints. Now, since we are including A as our decision variable now, so we must also impose the constraint on A, right? So this is the memory constraint that I talked about a few slides back. So now we are bringing in that constraint within our problem itself, so that we are forced to choose from only the set of feasible replication policies. So we cannot choose any A, but only those A's which satisfy this memory constraint for each server. Okay. So now for this problem, as I mentioned, both A and B are our decision variables. And we call this problem as the joint allocation and matching problem, or in short, JAM. Okay. So JAM includes both replication and matching as the decision variables. But still there is one problem with this formulation. It is not yet complete. The final step is to replace this random quantity. So we have an optimization problem, but we have this XC coming up here in this constraint. But we don't know what the value of XC is a priori, right? Because we cannot predict what would be the number of requests of a content within a unit interval of time. So that is a random quantity. So we must do something about this quantity. And the best way to get rid of this randomness is to replace this by the average number of requests within an interval. Now that is more predictable we can measure a popularity of a content, right? If we observe the request coming over a longer period of time, we can estimate what is the average number of requests that is given within a unit interval. So that we already have a notation for that. We called it lambda c, right? So so we can replace this quantity by the average of xc, which is lambda c. Why we can do that? It's because our goal is to really do well on an average. We don't want to do well in every unit time interval. So our goal is to do it well on average. So on an average within an interval, we would like to maximize the number of requests served. So that's basically this problem, joint allocation and matching problem, where we replace this constraint by lambda c, which is the average number of requests per unit interval. Okay. All right, so this is the problem that I would like to finally solve. So this is called JAM. I will refer to this problem as JAM. Remember this acronym. Now, if we can solve this problem, okay, so this is an integer optimization problem, because you see these variables are taking values within the set 0 and 1. So ASC can only take 0 or 1 value. So this is an integer optimization problem. And if we can solve this optimization problem in some way using some algorithm, then obviously it will give us the answers. So it will give us the replication policy A, which is the best, and it will also give us the matching policy B, with which we can completely design our system, right? But the problem is that this problem is not easy to solve. In other words, more technically, I can afford to be more technical here, because you're all computer scientists, so I can go more technical. So what we have shown in our paper is that this problem, JAM, is actually an NP-hard problem. Okay, so you must be familiar with the concept of NP-hardness, which means that it is computationally difficult to come up with an efficient algorithm that will solve this optimization problem. So no matter how well we code, it is probably not possible for us to come up with an algorithm that will efficiently solve this problem if we have, say, a large number of servers and a large number of content, so that the running time of that algorithm, or if you try to run that program of solving that problem, it will take a huge amount of time that you'll never able to complete the execution of that program. Okay, so we cannot find, because it's an NP-hard problem, we cannot find such an efficient solution. And how can we prove that this problem is NP-hard? This is a mathematical statement. To prove that, we basically reduce our problem in our previous slide. So this is the problem I had. This is what we called the JAM. But we show that this problem is actually equivalent to another optimization problem, which can be written like this. Okay, here I have replaced ASC and BSC by this single optimization variable ZSC, and I'm imposing some constraint on ZSC. And we optimize this objective function, and it turns out doing this or solving this optimization problem is exactly equivalent to the JAM problem that we discussed before. And if we find an optimal solution, Z star, of this problem, from there, we can compute the optimal allocation policy simply by doing ASC star equals, by setting this equals to indicator of whether ZSC star is positive. So this notation means that ASC will be set to 1 if the corresponding ZSC is positive. Okay, so this is once we find the optimal ZSC, from there we can easily compute the ASC, optimal ASC. But this problem, we have shown that this problem is actually NP-hard. And how do we show that? We use the 3-partition problem, which is already a known NP-hard problem. And we show that this problem is equivalent to this 3-partition problem. And therefore, it cannot be solved efficiently. Okay. So there is no algorithm which can solve this particular problem. So what do? Are we stuck then? So we attempted to solve a problem. We formulated the problem, and it turns out that it's too difficult to solve, right? So should we stop here, or should we look for some solutions still? So the answer in this case typically is that as computer scientists, we never give up. We have to still try to find a solution which may not be the optimal solution, but at least if it is close to the optimal solution, then we are good. Okay, so there are many NP-hard problems in the world, but most of them can be actually solved quite efficiently, in the sense that they might not give you the exact optimal solution, but we can have a very close to optimal solution. And that's exactly what we'll try to do. We'll try to construct solutions that are close to optimal, or we will try to come up with algorithms that can give us solutions that are close to optimal. Okay, so this is the goal of the next few slides. So I'll try to construct an algorithm that will not give us the optimal solution, but give us a solution which is probably close to the optimal. Okay, so how do we do that? The first attack, or for any computer scientist, is to tackle the problem with a greedy approach. Okay, so the greedy algorithms is, as the name suggests, we try to be greedy. So we try to match the request to the servers in a greedy way. So as I mentioned here, so this is the equivalent problem, right? So we are trying to solve the jam, and therefore this is the equivalent problem to jam. And you can see that we have this variable ZSC, and what we are trying to do here, so we are trying to maximize this sum over here, such that it satisfies both these constraints and also this constraint over here. Okay, so what we do is we are proposing this particular greedy algorithm, where we pick a particular content on this side, and we pick a particular server also on this side, and we try to match those. Okay, at every step we pick a server, pick a content and pick a server and try to match those. So how do we select the server and how do we select the content? So we, at each step, we select the content which has the maximum remaining value of lambda c. So remember that we have to satisfy. So there are, we can sort of consider edges. So this can be thought of as a bipartite graph or bipartite network. So we can think of edges connecting these servers to those contents, and we can assign weights to these edges. Okay, so these are called ZSC, and these are our variables, optimization variables. Now the edges that are emanating from a particular content, for example, for this content, we have these two edges that are coming out of this particular node, and the sum of these two edges, or the weights of these two edges, must be less than lambda c. Okay, and so therefore, and similarly, the sum of the weights coming out of a particular node on the server side must be less than US, because of this constraint here. And also we have to satisfy this third constraint, which says that the number of edges that come out of a server node that has positive value of edge weight must be less than DS. So the number of edges that are coming out which have a positive value of these weights must be less than DS. So that's the third constraint. Now, what is the greedy algorithm that satisfies all these constraints? We pick a content at each step. We pick a content with the maximum value of this lambda c, and try to match this with the maximum value of with a server which has the maximum value of US, because our final goal is to maximize this sum ZSC, right? So we want to choose these edge weights as maximally as possible without breaking these constraints. So that's the greedy approach that we will take. So this is the flow chart that shows our algorithm. So basically what we call as flow is exactly the quantities US and lambda C. So for each server S, we initially assign the flow of S as US and flow of C as lambda C. And we also assign a degree to each server, which we call DS, which is the memory constraint of that particular server, DS. And then at each step, we find the server which has the maximum flow among the servers which has a positive degree. And we also find the content which has the maximum flow left. Okay. So this is the C star content. And then we find the ZSC that we can assign to this particular pair, server content pair, by finding the minimum of these two quantities, flow of S star and flow of C star. And we set the corresponding allocation to 1. So we allocate that particular content to this particular server at this particular step. And we keep on going, and we keep on repeating these steps until we exhaust our possibilities. So in other words, until we reach the condition that there exists an SC pair such that this quantity here is positive. Okay. So if we find no pairs which satisfy this constraint, then basically we stop our algorithm at this point. So that's the terminating condition. So this is our greedy algorithm in short. But obviously this is not the best algorithm. This will not give us the best optimal solution for the problem, for the jam problem. But how close can we get using this greedy approach? That's the question that we have, right? So for this greedy approach, first of all, what is the complexity of the greedy approach? It can be shown easily that if the number of contents is n and the number of servers is n, then and the number of contents is m, then the complexity of this algorithm is of the order of n plus m squared. So it's a polynomial time algorithm. So it's very efficient to implement as a computer program. And what we show in our paper is that it is a two approximation algorithm for jam. In other words, it means that although it is not able to find the exact optimal solution, the solution it returns is going to be within a factor of 2 of the optimal solution of the actual jam problem. Okay. So it is guaranteed that whatever solution this greedy algorithm returns is going to be within a factor of 2. It's never going to be more than a 2 factor away from the optimal solution. So that's how accurate our approximation algorithm is. But you may argue that the 2 approximation is not a very good approximation, because a factor of 2, if you are away from the optimal solution by a factor of 2, it's not a very good algorithm, because we might still be far away from the actual optimal solution, right? So you're right when you say that, and we will definitely try to improve further on this. Okay, but I will come to that later on. So this is our greedy algorithm that I just described. But is it the only algorithm? Obviously not. We can have other algorithms, but for those algorithms, we may not be able to guarantee things like, for example, it will always be within a factor of 2 and so on. But we can always come up with more heuristic algorithms. And one such heuristic algorithm is called P2P, or proportional to popularity. This is a very intuitive algorithm. So what it does is that so we are trying to decide the replication algorithm, right? So we are trying to decide which server will store which contents. Now, a particular server which has DS as its memory size cannot store more than DS contents, right? Now, which of the DS contents can we store at a particular server? That's the question that we are interested in. And this particular algorithm, what it does is that it selects a set of size DS. So I select a subset K from the set of contents C of size DS with probability which is proportional to the popularities of the contents belonging to the set K. Okay, so with that probability, I will assign that particular set of contents K to that particular server. Okay, so this is our proportional to popularity scheme. So when I assign a subset of contents to a particular server, the probability with which I do so is going to be proportional to the popularities of the contents belonging to that subset, which is very intuitive, right? So that this basically will ensure that the most of the server will have the popular contents. So the popular contents will be replicated in more servers than unpopular contents. Basically, that's the intuition for behind this proportional to popularity scheme. Okay, so this is one algorithm which is based on our intuition of how ideally we would like to allocate the contents to the caches. And another heuristic scheme is called uniform scheme, or in short, we will call it UNIF. And UNIF is basically assigning, or it's basically treating all the contents to be equally popular. Okay, so that means that all the lambda C's, although they are not equal, but we'll treat them as if they're equal, and we will assign any subset of size DS. Okay, so how many subsets are there? So M choose DS, that many subsets are there from since M is the total number of contents and DS is the size of the server or size of the memory. So we choose DS number of contents in this many different ways, and each such subset of size DS is equally popular. So in this case, so the probability of assigning a particular subset of size DS is equal across all subsets. So all subsets of size DS will be assigned to that particular server with this probability. So that's why it's called uniform, because we are not really distinguishing between the popularities of the contents. Why we are doing so? Because it's simple to do, right? Because we don't need to know the popularity of the contents to allocate the content. So we can just randomly assign the contents to the servers. To implement this scheme, it's easier because we don't need to have estimates of the popularities. That's why this is also another possible approach that we can take. And this will serve as a baseline for our comparison results. When we come to our comparison results, we'll show the comparison of this other algorithms like P2P and the greedy algorithm, and we'll show how it differs from the UNIF algorithm. Okay. All right. So these are the three replication algorithms. But what about the matching algorithm? Remember again that we had two knobs at our disposal. We can turn both the knobs. For the past few slides, I've been discussing only about one of the knobs, which is our replication algorithm. But we assumed, for these few slides, for the last few slides, we assumed that our matching algorithm is basically the maximum matching algorithm. So if you remember the problem that we discussed first, even before introducing the jam problem, I discussed this matching problem where I give the replication algorithm A and I ask what would be the best possible matching algorithm. And I said that this problem is easy to solve and that is equivalent to the bipartite matching algorithm or bipartite matching problem, for which we already have efficient algorithms. So for example, if we give this replication algorithms, for these algorithms, we can correspondingly find a bipartite maximum matching, and we can use that as our matching policy. That would be the best possible combination. So we fix this allocation policy, and corresponding to that, we find the best possible matching by solving the bipartite matching problem, and we use this combination. There is no problem in that, except the fact that actually this maximum matching algorithm, which we already know about, which is the bipartite matching algorithm, this is actually not very useful in the context of content distribution networks. Now I'm going to explain why is it so. Why is it not suitable for our systems? So this is why. Suppose this is a toy example, but this is enough to explain the concept. Suppose we have this system where we have these two servers on this side, and there are three possible video contents, A, B, and C. Okay, this particular server is able to store only contents A and B. Okay, and this particular server stores the contents B and C. So we have already decided the replication algorithm. So we have already populated the memories of these servers. So I have stored these A and B contents at this server, and B and C contents at this server. Now suppose at a certain instant of time, we already have one request of content B and one request of content C being served by this server and this server respectively. Now remember that there are bandwidth constraints as well. So this I assume that this server can serve at most one request at a time, and this server can serve at most two requests at the same time. Okay, so now at this point, suppose this is the snapshot of the system at a given instant. Now suppose a new request of content A arrives. So user request comes for this particular content. So what can we do about this new request? Note that this content is only stored in this server, but this server is already serving another user, right? Because this edge is already there. So it is already serving another user, and it cannot serve more than one user at a time, because that's the bandwidth constraint. So what can we do? Because this content is not stored in this server. So if we have to serve this user, we have to use this server, right? So, but since this server is already serving this particular user request, we have to break this connection and assign this request to this server. Okay, so this is exactly what is done in this snapshot. So we break that connection between B and this server, and we assign that request to this server, because this server also stores B. So this request can still be served by B. And if I break this connection, then I have one room. I have created a room for this new incoming request. And this request now can be assigned to this server. Okay, so I have to do this breaking of the connection while it is being served. And this is not at all ideal for a ongoing connection, because we have to keep track of how much progress had been made on that particular request and so on. So it really is a complicated thing to implement during during the time when the request or the user is being served the request. So we would like to avoid such repacking of requests. So this we call as repacking, because we are somehow packing the request in a different way in order to do this, in order to allow this new request to come in, right? So the maximum matching algorithm that we were assuming so far, although it can be computed easily, we know the algorithm, a maximum matching algorithm, but the maximum matching algorithm, whenever it sees a new request and it cannot see a available server which can take that request, it can potentially break requests, like break ongoing connections like this, and then accommodate new requests. So that's a problem of the maximum matching algorithm. So we would like to get rid of this problem, or we would like to avoid this type of problem in a caching system. And another problem with the maximum matching algorithm is that we have to, so if there are, so here I have only considered 2 servers, which is a toy example, as I said before. But in a real system, there are like thousands of servers. And in order to implement the maximum matching algorithm, we have to basically know the state of every server in the system. So we have to know what each server is storing, and we have to know which server is storing, which server is serving which users at a given instant. And if there are so many servers and so many requests, it is not easy to know, this whole system state at every arrival at every new arrival instant. We cannot probe every server to know what state they are in, right? So that's not computationally feasible. So therefore, these are the 2 problems. One is that it requires, the maximum matching algorithm requires repacking of the requests, repacking of existing requests, which is not feasible, which adds overhead and delay to the process. And another problem is that it requires the state of every server in the system, which is also an expensive thing to know. So what is the alternative? An alternative, a much simpler alternative, is proposed by us in the paper, and we call it the random available server matching algorithm. So what does it do? It's very simple. It basically, whenever a request arrives, it will pick at random a server which stores the content. Of course, the server has to store the content, otherwise it cannot be served at that server. And secondly, which is able to serve an additional request of user. So this algorithm does not require any repacking of the existing request. I will assign the new request only if a server has room for that additional request. Okay, so that basically simplifies my algorithm. So it will not cause any repacking of the request, and it will also not require us to know the states of all the servers. Why? Because whenever a server sees that I am not working at my full capacity, it can itself, it can let the content distribution operator, network operator, know that, well, I am now available to take more requests. So the operator does not require to probe each and every server to know its state, but the server themselves can let the distributor know that I'm available to take more requests now. So at a given instant, when a request arrives, all the operator needs to do is to see the list of available servers, and among them choose any one of them at random, and route the request to that particular server. Now, obviously, under this algorithm, we will have cases where an incoming request cannot be matched, because we might not have an available server which is able to take additional request when that request has arrived. So those requests will definitely be rejected from that system, and they will go to the main server to be processed, right? But we would like to minimize the fraction of such requests, right? So that's the goal. That's our original goal. So now the question is, if we combine this matching algorithm with the replication algorithms that I described before, what would be the performance of the resulting system? So we had 2 knobs. Now we have fixed our knobs at these two particular things. So we have selected one particular replication algorithm, and we have also selected one particular matching algorithm. So under this combination of knobs, the question is what is the performance of the system? So to answer this question, now so far we haven't talked about the asymptotics of the system, and we were only considering a finite system. In other words, we were assuming that the number of servers is finite, the number of contents is finite, and so on. Obviously, this is for a real system, it is always finite, but the numbers are really large. Okay, so we can mathematically, when we are trying to solve this problem, we can let these quantities go to infinity and then tackle this problem. And this is called the asymptotic behavior of the system. And this is what precisely I'm going to talk about now. So what we are going to do is that we are going to scale the system up. By that, I mean that I'm going to let the number of servers go to infinity. So why would we like to do that? First of all, the real system is like that. It has huge number of servers. So mathematically, letting n go to infinity does actually gives the right regime or right limiting regime to start analyzing the system. Okay, so that's the proper thing to do. And secondly, as we shall see soon, it actually simplifies the analysis, or actually we can, so we saw that for the finite system, it is actually computationally impossible to come up with the actual optimal algorithm. We can only do approximation algorithms, but we can never do an exact algorithm for the finite system. But as I will show, we will be in the limiting regime when we let n go to infinity, when we let the number of servers go to infinity. It turns out that the problems become simpler, and we can actually come up with exact optimal algorithms. We don't need to do approximations. With just a combination of simple algorithms, simple allocation and matching algorithms, we can actually reach the optimal system performance. So that's the beauty of asymptotic analysis. So although we have, for the finite system, we have a very complicated problem, which is hard to solve computationally, as n goes to infinity, it becomes an easier problem to solve, and we have good algorithms, simple algorithms to solve the problem. So this is what I'm going to discuss briefly. I'm not going to delve deeper into the mathematical details, as it would be not feasible to do in this talk. But I will just give you the overview of the results. So we let n go to infinity. Remember, n is the number of servers. And as we do so, we have to also scale up the arrival rates, right? Because we are, I mean, in a practical system, why would we like to increase the number of servers? It is because the demand is more, right? So the popularities are also increasing. So we cannot keep the popularity the same and increase the number of server, because that doesn't make any sense. So we are scaling also the popularities of each content. So remember, lambda c was the arrival rate of a particular content c, and we are scaling that up also by the same factor n. Okay, so that's that's how we are scaling the system. And under this scaling, this ratio of the total arrival rate of all the contents taken together and the total bandwidth capacity of all the servers taken together, this remains invariant. So although we are increasing n, the ratio between the total rate at which contents arrive and the total capacity of the system, or the bandwidth capacity of the system, that ratio remains constant. We are not changing that. We are only resizing the system, keeping this ratio constant. So that's what the scaling really means. Now, we can so we denote this ratio by this letter rho, the Greek letter rho, and we can show, it is easy actually to show by some preliminarily probabilistic techniques, we can show, I'm not going to discuss though, but we just take my word for it, that the maximum achievable performance of a system is given by this quantity here, this quantity min of 1 comma rho. Okay, this is the maximum achievable acceptance probability. So that means when a request arrives, so we would like to ensure that request is actually served by the system, right? So we want to maximize the probability of a request being served by the system. So, and it is possible to prove an upper bound on this probability, and this upper bound is given by this quantity min of 1 comma rho. Okay, and this is equivalent to saying the minimum blocking probability, which is the reverse of that. So the 1 minus this quantity is basically the blocking probability. This is the probability with which the request of the user is blocked or rejected from the system, and therefore it goes to the main server. And this is just 1 minus this quantity, and this is basically the so this is the maximum acceptance probability, or 1 minus this quantity is the minimum blocking probability. So this is this quantity. It can be shown that 1 minus this is actually 1 minus 1 over rho, the positive part of this. So this means that when this quantity is positive, we take 1 minus 1 by rho, but if it is negative, we take the value to be 0. Okay, so that's basically this is the lower bound on the blocking probability, or the upper bound on the acceptance probability. Now, if by turning the knobs we can somehow reach this upper and or the lower bound, that means we have achieved optimality. Okay, so this is we don't know yet. We know that these are the bounds, but we don't know whether we can achieve this bound. And I will show that using our previously discussed matching and replication algorithms, we can actually achieve these bounds when we scale up the system like this, when we let n go to infinity. And this is exactly what we have established in the paper under certain assumptions. Obviously, when we state a mathematical theorem, there needs to be some assumptions made on the system, and we also have some assumptions. Our assumptions are a little bit technical. I'm not going into the details. So we'll assume that the arrivals are according to Poisson processes, and our service times are according to exponential distribution. Okay, and under this assumption, although I'm going to relax these assumptions later on when we discuss the simulation results, but under these assumptions, theoretically, we are able to show that these combinations of greedy replication algorithm with the RAS matching algorithm. So RAS, recall that it stands for the remaining available server algorithm. So this is the algorithm that we designed in our paper. So this combination of greedy replication plus RAS matching algorithm, and also the combination of proportional to popularity P2P replication and RAS matching algorithm, both these combinations actually can achieve the minimum blocking probability as n goes to infinity. So as we scale up the system, these combinations will achieve the minimum possible blocking probability. So that means this is the optimal system performance as we scale up the system. Now, obviously, we don't have a system which has infinite many servers. Obviously, that's not real. But since we are operating in a regime where actually the number of servers is pretty large, this result is of very high importance, because it says that in that regime, when we have a large number of servers, these simple algorithms can be very close to the optimal or to the best performance that is possible. Okay. So here are some steps of the asymptotic analysis, but I'm not going to discuss these slides because these are more for technical audience. I'm not going into the details. But this uses something called the mean field analysis. And this is a technique from probability theory and stochastic processes. And using this, we can show that this theorem indeed holds. Okay. So I will jump right to the simulation results that we have for this system. So here, what we are plotting in these two graphs is the average loss rate. So this is the blocking probability. I'm just calling it by different names everywhere. So this is nothing but the blocking probability. And we want to minimize the blocking probability for this system. And the lower the blocking probability, the better it is. And we are plotting the blocking probability as a function of the number of servers in the system. So we are increasing the number of servers, and we are seeing what is the blocking probability under these combination of replication and matching algorithms. So in this pink line, we are showing the combination of UNIF algorithm with RAS. The black line shows the greedy with RAS. The red one shows the P2P with RAS, and the blue one at the bottom shows the lower bound. That's the theoretical lower bound. That is the best possible lower bound for any combination that is possible. And we see that as n goes to infinity, really all these combinations, these black and red combinations, they are actually converging towards this blue line, which means that they're actually converging towards optimality. And this is what we mean by the asymptotic property of the system, or the asymptotic property of the algorithms. So under these two algorithms, the system actually converges to optimality as the number of servers increases. But you see here that this combination of UNIF algorithm with RAS is way worse than these algorithms. So this particular combination never reaches optimality. It's far away from the optimal results here. Okay. And this is a scenario for row less than 1. And this is another scenario for row higher than 1. And we see the same thing. Again, we see that this red and the black curves, they both converge to the minimum possible line, which is the blue line. But the pink line here is way above, which means that it is never reaching the optimality, even as we let the number of servers go to infinity. Okay, so and this table basically shows what is the speed of this convergence. And we show that this is roughly the convergence speed is of the order of n to the power minus half, so of the order of 1 over square root of n. So that's the rate at which this curves actually converge to this blue curve. So that's this table is just to show that the speed of convergence is of the order of this. So that's one result. And the third result is on the relaxation of the assumptions that we made to state the theorem. Remember that we said that the service times distributions need to be exponential in order for our theorem to be valid. But in reality, when we change this service time distribution to other distribution like constant, log normal, or Pareto, we see that there is very little change in the actual results. So in other words, we see that for this value of n and rho, we see that no matter what service time distribution we take, the values are really very close to each other. Okay, so there is no really difference between these different columns. And that leads us to conjecture that indeed, although our theorem is derived assuming the fact that we have the specific distribution, exponential distribution for the service times, we don't need that assumption. They're probably valid also for other distributions, but this is not yet proved. We have shown something similar for other systems, but for this system, still it remains as an open problem. Okay. So this is another plot I'm not going to discuss here because it's not so important in this context. Okay, so this is the summary of what I have been talking about so far. So, so what we have seen so far, just to summarize, so we have looked at the performance of a caching system or a content distribution network, and we tried to optimize this performance of the system as a function of two things. One is the replication algorithm, and another is the matching algorithm. So we first formulated a problem, a joint problem, where both the allocation or the replication and the matching were two parameters which we can tune to optimize the system performance. And then we showed that it was a hard problem to solve. And then we proposed some approximation algorithms which has some provable guarantees. So we showed that it is always within a factor of 2 and so on. But then we showed that in fact, those approximation algorithms are not anymore approximate when we scale up the system size. So as we scale up the system size, those approximation algorithms in fact become optimal algorithms for the same system. So that's in gist of what I have talked about so far about this system. So there are many interesting questions for future research. For example, in this particular talk, I have only described what happens when I scale the number of servers to infinite. But what happens if we also scale the number of contents to go to infinity? So that's still yet not clear. We don't know what the answer to that is. Another question is, what is the effect of network topologies on the performance? So that means here we have assumed that each server is each server is basically connected to all the other servers. It's a complete graph in some sense. But in case we have a network of cache servers where a particular server is connected to another particular server, so in that case, what will happen to the system? This is also still an open problem. And the third interesting question is to show that asymptotically these systems are insensitive to service time distribution. This is what I described in the last slide, that although I stated the theorem for exponential service time distributions, this theorem seems to be valid, at least from the numerical results that we have. It seems that we will still have the theorem to be valid even for distributions that are not exponential. So, so this basically concludes my my discussion on this particular problem on caching system. So I'll just see if there is any question on this part so far. So actually, I think I would probably, because I had some more slides to discuss, but I think it would be probably best to stop here because I'm already running out of time. So probably I can just take your questions at the moment, if there is any.
Sir, good evening. This is Joy Bandhavadar from Electrical Department.
Yes.
So I would like to place the questions. Those have been put up in the chat box. Like first question is the telecommunication network infrastructure able to support the increase of renewables and still perform correctly?
The telecommunication network, yes. So basically, the grid network is different from a telecommunication network. But in today's world, we are seeing increasing penetration of renewables. So what we use today to support renewables is called smart grids. So smart grids means that there are smart meters installed at different points. And these smart meters are part of the communication infrastructure, not the grid itself. So the grid operates as a separate thing, but the communication infrastructure is also separate. That's the telecom infrastructure. The only case where they intersect with each other is where we are using a smart grid and where we are using smart meters and so on in these grids. So they can communicate with each other to transmit meter readings and so on to efficiently control the use of renewable energies in the smart grids. But it is to answer your question, yes, it is possible because these are different networks. Telecom networks is different from smart grid networks. And indeed, we have practical examples of smart grids that are employed at different places in the world, including India and other places, where we have smart meters installed in renewable grids, and they are able to support renewable energy installation as well. Yes.
Thank you, sir. Then another question is the current regulation mature enough to handle, to enable new concepts and attract new business models, or does the regulation need to change drastically?
So, so which regulation is
Current,
referred to?
the current present regulation is talking about. The present regulation of this telecommunication network, is it mature enough to enable new concepts? I mean, like any kind of modification or hybridization, can it be done to attract new business models, or it is a rigid one?
So it is not easy to answer this question, because businesses are attracted by different terms, that these are not necessarily technological aspects, but there is an aspect of profits related to this, whether businesses will be interested in certain regulations or not. But it has been also analyzed in the technical domain, whether regulations like net neutrality and so on are actually in favor of businesses, or they're actually in the opposite, or they actually discourage businesses. But there are arguments from both sides. Actually, it's some argue that net neutrality policies or regulation policies are actually, they need to be enforced in order for small and medium businesses to flourish, because if you favor the large businesses, for example, like Facebook or other big tech companies, they will occupy the entire online marketplace, and therefore no new business will be able to compete with them. But with the net neutrality policy, we can actually encourage even small and medium scale businesses. So yeah, so basically, but there are arguments on the other hand as well, so which say that these policies are not good for businesses or new ventures and so on. But one can argue in both ways. So there is no definitive answer really to that question.
Thank you, sir. That's clear enough. These were the only two questions that have been put up, sir, in the chat box.
Okay.
So with this, I would like to present my vote of thanks. Good evening, everyone. Myself, Joy Bandyopadhyay, and I am the Senior Assistant Professor in the Department of Electrical Engineering at Surendra Institute of Engineering and Management. And I am here to present the vote of thanks for today's webinar. I would like to thank our respected Chairman, sir, Director ma'am, Principal sir, and our guest webinar speaker, Ms. Dr. Arpan Mukhopadhyay, for enlightening us with his knowledge. And today's webinar was full of knowledge, and definitely many interesting things were covered here. And it gave deep insights into the topic and also revealed some interesting facts. So I'm pretty sure that this precious knowledge that Dr. Arpan Mukhopadhyay gave us will definitely help us in our studies and future. So I would like to say thanks to all the active panelists and participants also. And attendance link has been presented. It is given in the chat box. So kindly go through the attendance link. Please click on the attendance link and just fill up the necessary required fields, and you will get your e-certificate. So thank you, sir.
Thank you very much. I was delighted to have been invited here, and it was, I hope that we have some contacts even in the future. Thank you.
Sure, sir. Sure, sir.
And lastly, we can go for a group photo. I request all of you to switch on your video so that we can go for a group photo. Okay, thank you all. This is a very nice and informative session. Thank you, Arpan Mukhopadhyay sir. Thank you, Principal sir. And thank you all respected HODs to be cooperation for your cooperation. And
Okay.
the students, you can fill the attendance form. Okay. After filling, you will get the e-certificates.
Okay. Thank you then. Bye.
Thank you, sir.
Thank you, Arpan sir. Okay.